The special purpose machinery market is due to grow by over $12 billion globally by 2022. So now more than ever, it's important that designers and manufacturers look at ways to improve time to market, reduce costs, and produce more innovative machines. And the easiest way to do this is by modernising your product development processes and tools. Development of special purpose machinery historically relied on 2D CAD tools, but the very nature of industrial machinery involves a significant number of moving components and mechanisms. Therefore, a 3D CAD tool is much better suited to this type of industry. Over the last 20 years, Solid Solutions have provided SolidWorks 3D CAD software to numerous designers and manufacturers of special purpose machinery. And throughout the course of this video, we will look at how a selection of our customers use SolidWorks to address some of the most common challenges faced by the industry. Being able to get a product to market quickly is crucial in a competitive marketplace, so any time saving that can be made during development enables designers and manufacturers to be one step ahead of the competition. The creation of a new design has many stages, from initial concept through validation, manufacture and inspection. Reducing the time it takes to create that initial design is the first area where some large savings can be made. SolidWorks has a wide range of tools designed to do just this. The creation of parts and assemblies in SolidWorks is streamlined through industry-specific features. Sheet metal tools allow for automated flat pattern development. Welded structure tools can add corner treatment and create cut lists. And libraries allow for quick leverage of standard components. Even piping, hydraulic tubing, and electrical cabling can be automated. Creating a 2D drawing is as easy as dragging and dropping a view. Section and detail views, exploded assembly views, bills of materials and balloons can all be created in seconds. And the best thing is that because a SolidWorks 2D drawing is driven from a 3D model, any design changes in the 3D are automatically updated in the 2D, reducing costly mistakes as a result of out-of-date drawings. One of the most valuable benefits that the 3D CAD system adds over a 2D CAD system is the ability to interrogate designs for interferences and collisions. The ability for greater validation during the design process not only results in a better quality product, but ensures that problems during manufacturing are kept to a minimum, reducing time, reducing material wastage, and reducing rework. We understand that one of the most expensive aspects of the design process can be centered around prototyping. The ability to check for collisions and interferences within the 3D design environment not only allows for more informed design decisions to be made, but it also highlights manufacturing issues before they arise. SolidWorks simulation can also be used to reduce the need for physical prototypes by analysing components for stress, strain and deflection. Designs can be optimised by selecting less expensive or lighter duty parts, or removing unnecessary material to reduce cost and weight. And all of this functionality is seamlessly integrated into the core design environment, removing the need for additional software packages. For any product, the design process often isn't linear. Customer requirements, new technologies, and even availability of raw materials can mean that designs may need to be modified at any stage of the process. I'm sure that every designer at some point in time has heard the phrase, "Can you just?" Can you just increase the size of this bend radius? Can you just move the bracing on these legs? These are changes that sound small in principle, but the knock-on effect can mean that multiple other documents then also need updating. With SolidWorks, modifying a design is as easy as adding a new feature or entering a new dimension value. When these changes occur, all of your documentation, including assemblies, drawings, cut lists, and bills of materials, update automatically. This dramatically reduces design time and allows for more innovative products to be delivered on time and on specification. Successfully communicating design ideas with key stakeholders is a critical part of the design process, and this becomes even more important when the proposed design is a brand new concept, such as a bespoke piece of packaging equipment. Ideas need to be shared and reviewed quickly and easily, and this is something that within a 2D environment is difficult to achieve. This is primarily because industrial machinery concepts are three-dimensional, and communicating these ideas solely within a 2D drawing often leads to misinterpretation. SolidWorks 3D models are easier to visualize and easier to understand than a 2D drawing. Having the ability to rotate a model in a 3D space or visualize a model as if it were a photograph is a much more natural way to view a design. It makes design accessible to everyone, irrelevant of whether they work in sales, marketing, purchasing, or engineering. And of course, not everyone needs SolidWorks to be able to view this information. With SolidWorks Visualize, 3D models are brought to life through photorealistic images, animations, and interactive content. And with eDrawings, SolidWorks' free viewer, 2D and 3D designs can be shared with anyone. Design is just the beginning of delivering a piece of equipment successfully to a client. But the information created at this stage can be reused again and again throughout the entire process of a project. Traditionally, the design engineer puts down their ideas to 2D, and this information is then handed to production, who begin to develop the machining, bending, and cutting processes required. Although this method has worked for many years, it does separate design from manufacture, whereas if the two were more closely linked, the result would be a more efficient, less error-prone process. This is where the additional benefits of a 3D CAD system come into play. The need to redesign, rework, and redraw components specifically for manufacture is no longer required. With SolidWorks, there are powerful CAD/CAM solutions linking the 3D design directly to the machines on the shop floor. This removes misinterpretation of a 2D drawing and also means that when a design changes, the toolpaths and manufacturing processes update too. The design of special purpose machinery often involves many designers working on multiple parts and assemblies. So managing the high volume of files generated can be intricate and time-consuming. Part of the SolidWorks solution is to provide data management software called SolidWorks PDM. SolidWorks PDM allows for efficient design collaboration, even when working across multiple sites. Its advanced search, data import, and configurability allow organizations to create custom workflows that manage revisions and make it easier than ever to retrieve and modify previous design data. For those projects that are a variation of a standard product or previous design, recreating all of the required design documentation from scratch isn't the most effective use of time. Being able to reuse existing data by simply modifying a dimension or adding in an additional bracket dramatically reduces the time it takes to get designs to manufacture. SolidWorks provides capabilities to automatically create and store numerous configurations of the same design. So when a design is modified, all the necessary drawings, bills of materials, cut lists, and flat patterns are instantly updated. With just a few simple inputs, thousands of machine variants can be created and stored from a single base design. In summary, SolidWorks software provides industry-specific tools and capabilities to minimize development time, lower development costs, and reduce design errors, ultimately helping to increase what really matters: product quality, customer satisfaction, and profit margins. Let's take a look at SolidWorks in action to see how everything we've mentioned so far works in a real-life scenario. We're going to start off the demonstration by looking at a model provided to us by Riggs Autopack. And the example that we will be working on is a semi-automatic depositor. This machine is used within the food industry as a means of filling containers such as jars, bottles, pots and tubs. and it dispenses suspended solid products such as jams, condiments, dips and dairy products. All of the files we're working on throughout this demonstration are stored within SOLIDWORKS PDM, and we'll touch on this some more as we work through. Special purpose machinery uses a number of manufacturing techniques within its products, and we're going to cover a few of these. The first is looking at a machine part, and this gives a really good grounding in the basic principles of 3D design within SOLIDWORKS. This subassembly is a cut-off valve plunger and needs an additional component creating and adding to the design. So we're going to start a new part file and capture the key geometry of our design. Now, any part file inside SOLIDWORKS starts life as a sketch, and this is the area where we capture the key characteristics of our design. We have a number of tools available to us, such as lines, arcs, circles, rectangles and slots. But the main difference with sketching inside SOLIDWORKS to any other CAD system is that we don't really have to pay any attention to how big we draw things. The actual size of the product is defined as a secondary process, and we do this by adding a number of different dimension types. I'm capturing 2 or 3 different diameter dimensions here. We've got some angled dimensions, as well as some standard linear dimensions too. Finally, let's just capture the height of this overall component. We're now going to turn this into what's called a feature. Now, there are a number of different features inside SOLIDWORKS. The one we're using here is something called a revolve, which takes our sketch and basically spins it through a full 360 degrees. We can add additional features which don't require sketches, such as fillets. We're going to add a few of those in here, maybe a 2mm fillet on that internal and a 1mm fillet on this external, just to get rid of some of those sharp edges. We can also add in chamfers. Now, you'll notice that a lot of the commands I'm accessing are actually on flyout menus, so we're not having to constantly bury ourselves in drop-down menus. Now, the next feature we're going to add is something called a library feature. Now, this is a piece of information that you may want to use over and over again on different designs. Rather than having to redraw it every time, it simply sits in a library and we can drag and drop it in and reuse it when required. So really quick and easy for common features to be placed. Let's add in one final chamfer, and that's our part pretty much modelled. We're just going to add in a few additional pieces of information, and the command we're going to use here is something called the hole wizard. So for anyone who's specifying hole types to standard, such as counterbores, countersinks, drill holes and tapped holes, this would be the tool to use. Rather than having to know all the information about that particular standard, we pick it from a pre-existing library, and all we actually have to do is position the holes in the screen. So I'm placing 2 M8 tapped holes here. One's going to be 10mm from the top face, and then we've got a 24mm spacing. And you'll see that it actually adds in all that information for us. Gives us the major diameter of the thread, the through hole, and also a visual representation of the cut as well. We can look at some of the mass information for this component. So we've just applied aluminium there, and it gives us the weight. If we then obviously change the material type and reanalyze, it's going to give us a different weight. So this is a live value which updates automatically. All of the dimensions can be changed at any point in time. So if we want to increase the height of this component, we simply click on the dimension and it does that for us. We're going to add in some internal thread detail, which gives us that visual representation of a thread and also the major diameter. So finally, we'll save this part file away back into our PDM system. We'll firstly give it our file name and part number, and then also our description, which in our case is a cylinder housing plunger cutout valve, and we'll click save on that. That's our first part created and saved away in SOLIDWORKS PDM. And that should highlight just how quick and easy it is to go from a blank sheet of paper to a working 3D model with built-in intelligence that allows you to make modifications. But for most of you, a 2D drawing is still going to be the output type needed to either get the product into manufacture or communicate the design with suppliers and clients. So let's see how we go from a 3D model to a 2D drawing. So to create a drawing of a part file, we just have to tell SolidWorks that's what we'd like to do. We have a choice of a number of different templates, A3, A2, A1, etc. And these can obviously all be customized to your company standard. Positioning the views is as simple as dragging and dropping. Because the model is driving the 2D drawing, the software already knows what it looks like from the front, the top, the right, and an isometric view. In terms of dimensioning, you've got two options. We can use the same dimension tool that we used in the sketch environment and manually add the dimensions in, or we can actually import the dimensions that already exist from the 3D. This simply overlays the dimensions on the drawing views, and we've then obviously got the ability to move these around and manipulate them as required. Everything to do with style, whether it be colour, the types of arrowheads, the font that's been used, all of this is fully customizable and can be saved away in your templates. We can also add secondary views. So let's take a look at adding a section view. This is really quick and easy. You just draw a line where you'd like the model to be sectioned, and the software automatically works out what that cut face would look like for you. We can also equally add detail views as quickly. We simply draw a circle, in my case, of where I want the detail to be. The software automatically scales that view up and even adds a tag for me, so we know exactly where that information's come from. So that's our 2D drawing complete for the moment. Let's save that away and put it into our PDM system. Unlike traditional 2D CAD, where all of your time is invested in the 2D drawing, you can now see how with SolidWorks more time is spent within the 3D environment. And the 2D is very much a secondary process, with views, dimensions and annotations being able to be added in a few clicks. This is perfect for getting an idea down quickly, but some of the big time savings come when you need to modify that design. So we're going to take our component that we've just modelled and put it back into the assembly where we were earlier on. We're going to add in what's called a mate, which is basically a reference between multiple components. We've got one in there holding our newly created component in place, and we're also going to bring down this lower sub-assembly and also snap it to the top face. Now we need to make some evaluations of this assembly to make sure it's responding in the way we want it to. Internally, we've got our plunger sub-assembly, and we'd like to make sure that that's got the range of movement that it should have. So we're just going to section the model, and we can actually drag this plunger up and down. And we'd like to see whether it clears the outlet for the product. And you can see that currently it's just clipping on that hole. So what we're actually going to do in order to address this is modify our newly created component and increase its height from 60mm to 75mm. What that will do is update the part within our assembly, update the part itself, and also update the part's drawing. I'm happy with the drawing as it stands, so I want to share this with the client. And I'm going to do this using an eDrawing. An eDrawing is SolidWorks' free viewer, and it allows you to share data with anyone. So we can take our drawing, in our case, save it away, and it gives the client the ability to actually add additional notes and markup to the document too. So they could ask us, is this chamfer large enough? What's really nice about eDrawings though, is that we've saved a 2D drawing, but it actually embeds the 3D model as well. Being able to manipulate the assembly dynamically allowed us to see how there was an issue with the positioning of the plunger bore. And because everything in SolidWorks is associative, changing a single dimension updated our part, drawing and assembly. So you'll never find yourself in a position where you have an out-of-date drawing. Let's take a more in-depth look now at managing our data and adding our newly created part and drawing into the SolidWorks PDM workflow. Okay, so as we've already mentioned, PDM is a secure data management system where you can keep all of your SolidWorks and other documents. We're going to take our drawing and our part file and firstly check it in, which we can almost see as being a save into the PDM system. However, what we can then do as a further step is actually submit it for approval. So we can have a number of different workflows in the PDM environment. It might be that as a designer, you don't have sign off on creating new products. It has to go to an engineering manager. And that's what we're doing here. We're putting a note in of what we've done on this particular design. We're sending it to Andy, who's our approver. And that particular document, both the drawing and the part, then go into this pending approval stage, and you can see that the note updates on the drawing. So Andy will get a notification and it will be down to him to sign off on this particular design. So let's have a look at the workflows. We're just going to go into the administration for PDM, and these workflows are fully customizable. So I was in work in progress, that was my design stage. I've then sent that particular design to pending approval. And then obviously if Andy accepts that, it will go to an approved stage, which would potentially be a manufacturable stage for that product. Now let's just jump back into this assembly. We've brought some other components back in, which were previously hidden. And you can see that we've got an explode view here currently set up. Now we've obviously added a new component in, which was the body that we'd modelled. That's now sitting within the explode. And we just need to make a few modifications to get things into the place we'd like them to be. These explode views can exist within the 2D drawing, and it's a really nice way of being able to itemize all the components. So let's open up our drawing for this assembly, and you'll see that straight away in the view on the left-hand side, that newly added component gets positioned. And all we actually need to do here now is add in the additional balloon, which gives us our item number. And then if we come across to the bill of materials, which is in the top right-hand corner, you'll see that the component has been automatically added to that bill of materials too. So bills of materials in assembly drawing views are automated. As you add and remove components from an assembly, they will automatically update accordingly. For large complex designs, such as special purpose machines, storing your data, managing revisions, and making it simple to retrieve and modify designs is key, and SOLIDWORKS PDM allows you to do this really easily. We're going to step back into 3D modelling now and look at some of the more industry-specific tools that are available, including weldments and sheet metal. Let's open up this welded frame, which is currently part of our assembly, and you'll see that there's an existing sketch visible on screen. We're not going to redraw the sketch for this particular design, as we've already looked at sketching in the initial part model, but it's created in much the same way. We're going to add in something called a structural member. A structural member is basically a profile, and it's for anything that comes in length. That may be box section, it could be equal angle or unequal angle. The library already exists in the software, but you can add your own profile types in too. This particular design, as we mentioned, is for the food industry. So what we're doing with all of these profile types is rotating them through 45 degrees, which will create a runoff to stop any sort of food stuff getting stuck. We've got a number of controls we can add in terms of corner treatment. So we can say butt joins, we can have mitered joins, and even where intricate compound angles join each other within this framework, it will treat those and trim those for us as well. So let's just accept that feature off, and you'll see that it adds in all of those profile types. Now if we zoom in, it hasn't actually trimmed them lower members back to the structural members that already existed. So we've got some pretty intelligent trim tools, which again automate this trimming process. We select the bodies we'd like to trim, what we'd like to trim them to, and then you'll see if we hide off some of these bodies, the lower profile of this newly created member has got quite a nice intricate cut on the lower side of it. Now the real benefit of using the weldment tool is the fact that it automatically generates your cut lists. So we can see the cut list items here inside the part file, but let's take a look at the 2D drawing. Straight away, all of those new members get added into the views, and you can see that in the cut list, the 30 by 30 box section has automatically appeared as well. Traditionally, creating the cut list was very much a secondary process which was done independently to the actual design stage. In SolidWorks, the two things are perfectly tied together. If you change the design, the cut list will automatically update. Okay, so we're going to move on and take a look at some sheet metal design now. The hopper that already exists on the top of this frame has currently got an element to it missing, and we're going to use some of the sheet metal tools to finish this design off. So the tool we're going to use is something called the Convert to Sheet Metal. We've got the existing body on the inside, and we're actually just going to take the face of that body and turn it into a sheet metal part. So we'll firstly capture the initial bends that we're interested in, and then once we've captured those bends, we're going to use something called the Edge Flange tool to capture this return on the top edge. Now it's quite an intricate shape this, because it's not only a flange but it's also got these mitered corners, and we want to be able to match up the existing miters on the other two components to both the left and the right hand side. But we can do this using SolidWorks' intelligent sketch tools. We can add relationships to say that things are equal to each other, or in our case parallel, and that sketch automatically snaps into place. All we then need is one final dimension, and we've got the first part of our return flange. We're going to use the same tool again, just to bring the lower element of the flange down. In this instance, we can just say, go up to the same point that the other flanges do. So there's no need to put an additional dimension in. There are some extra pieces of detail we'd like to add here. On the outlet, on the base here, there's actually going to be a connector which sits on the underside of the hopper and takes it into the pipework. So we need to make sure that we've got a cutout for that. We're just going to draw in a circular sketch, again dimension it up, and we'll cut that through. When you're working in sheet metal, we can use an option called link to thickness, which means every time we add something in, it will automatically be the same size as the thickness of the sheet. It keeps things really easy, really quick and simple for when you need to make modifications. Okay, so I'm reasonably happy with that sheet metal part. Let's open up the existing drawing and take a look at that. Now you can see that straight away that new element to the sheet metal part gets populated in the views, and it also gets added to the cut list, much in the same way that it does with weldments. We've got a secondary sheet here which is showing all of the flat patterns. Again, one of the real great things about SolidWorks is that you can model a sheet metal part in the 3D and it automatically calculates the flat pattern for you. So in a couple of clicks, we've gone from a folded up 3D part to the flat blank that you'd need to maybe get laser cut or plasma profiled. So a massive time saver if you think of how long it would take you to do that if you're using a 2D package or maybe no CAD package whatsoever. That hole that we've added to the underside of the hopper, we can now see back in the assembly, and we're just going to locate that by adding a mate in, and that mate is going to link the lower piece of the pipework there to the underside of the hopper. Okay, the final thing we'd like to do on this is add in the casters. So currently we've got the lock-off feet that this framework is sat on, but this particular piece of equipment can be moved around, so it also has casters that are located on the underside. This would typically be something that you probably wouldn't model. A caster would come from a supplier, so SolidWorks has a really large supplier network from which you can download 3D models. And we've got this saved away in our library, and all we're going to do is drag and drop it in. So again, massive time saver, not having to draw every single component. You can download them, add them to your library, and then add them to the design as required. Cut from sheet and fabricated frameworks are so quick to model in SolidWorks due to the sheet metal and weldment tools that we've just looked at. These not only save you time up front, but you get the secondary benefit of having flat patterns and cut lists automatically generated and updated too. The final thing we're going to do is to validate and optimize our design by running a simulation on the framework that we've just created. So in reality, the weight that would sit on this framework would be as a result of the material of the hopper and any food stuff which is inside the hopper. Now, the material choice that we've made here is for a jam. So we've applied a density of jam, which gives us an overall weight of just over 160 kilograms. So let's set our simulation up. We've got a simplified version of this framework. We've just turned the end caps off to make it slightly easier to manage. And we need to give the simulation certain pieces of information. The first is going to be what's called a fixture, and that's where the model would be restrained in real life. So we're going to do that at the points where the lock-off feet would be, and there's 4 of those on the lower part of the frame. We're then also going to add our force. So this is our 165 kilograms, and it's going to be equally distributed across these 4 points. So we actually need to divide that value by 4 to make sure that we get an equal distribution across those 4 points. Now the force is going to act directly downwards, so all we have to do is select a plane to mimic that direction. And once we've got our fixtures in place and we've got our force in place, the final thing to do here is actually just run the simulation. So this is where the software does all the hard work for you. It's got all of the industry standard equations built into the software, and it will run those based on the information that we've given it. So we can look at a number of different plots. We've got stress here at the moment. We're just going to modify it so we can actually see the beams rather than them being stick outlines. We can look at displacement. We can also plot things such as factor of safety. So let's add in this factor of safety plot now. And you can see that the factor of safety for this framework is really quite high. So there's some potential for us to optimize our design. What we're going to do is reduce the wall thickness of the section that we used. So we're going to go with a 1.2 mil wall thickness rather than a 2. And because all of this sits within the SolidWorks interface, it's as quick as just toggling back to the modeling environment, making the modification, back into the simulation, and we can rerun it straight away. So there's no exporting and importing of information. It all sits really nicely in the core interface. And you can see that we've drastically reduced our factor of safety. Now, this is obviously a generalization. There's lots of other weights and bits of information that would sit on this frame in reality, but this gives you a really nice idea of the capabilities of SolidWorks simulation. It can also automatically create reports. So we're just going to tap in some information to do with the designer, which is myself and also the company, and it will publish this to a Word document. So it does all of the hard work for you. That brings us to the end of the video. Hopefully everyone has found it useful, and as ever, if you have any questions or you would like to find out more about SolidWorks and Solid Solutions, make sure to get in touch.